So previously we've discussed definite integrals. We defined them as the limit of Riemann sums. And we saw how the definite integral gives us the net area of the region bounded between the graph of a function and the x-axis. Well, since it's the net area, perhaps we can use geometry to find the area. So for example here, we are going to use geometry to compute this definite integral here. And of course it's definite because you have the endpoints defined there. So we want this value here. Okay, so take a look at A. Here goes the function 2x plus 3 in blue there. Its graph is shown there. And what is this telling us? Well, we want the net area between x equals 2 and x equals 4. Okay, we want the net area of the region bounded by this curve and the x-axis from 2 to 4. Well, let's use geometry to compute that. We'll break up this area into two different pieces, the triangle up here and the rectangle down here. The area of the rectangle is 2, which is the width, times 7, which is just this height here. Okay, we're leaving out the triangle, and that's 14. The area of this red region, this triangle here, we're going to use 1/2 base times height. It's a right triangle, so we'll use the formula 1/2 times the base, which is 2, times the height, which is 4, and we get an area of 4 for that red region. And so the definite integral there will be 14 plus 4, 18. Okay. Alternatively, we could have also looked at, used the trapezoid formula here with the two different bases and gotten 18 as well. Well, what about this guy here? Okay. We want the net area of 2x minus 6 from 1 to 6. How does that look? Well, here is how this looks. Here's the function 2x minus 6. That's this blue curve that you see there. And we want that net area from 1 to 6. So from 1 to 6. Well, there's part of it that's below the x-axis. That's going to give us a negative area in our net area, and part of it that's above. So the area that's below has it's a right triangle there, has a base of 2 and a height of 4. So that area is 4. And likewise, similarly, we could do the same thing here and get 9 for the area. And so what is the net area? Well, it's the area of the regions above the x-axis, which is 9, minus the area of the regions below the x-axis. So it's 5. 9 minus 4 gives us 5. Well, what about this guy? Here we have this function here, and you could see that it looks circular. Okay, so this is the, if we wanted to look at this as a curve, y is equal to square root of 1 minus x minus 3 squared. Well, then we could shuffle these things around here and get x minus 3 squared plus y squared equals 1. Okay, so this is this relation here gives you a circle of radius 1 at the point x equals 3, y equals 0. So that's what you see here. And we're only taking the positive root here. Okay, so this is the positive root. It is indeed a function. And so we have this function here, and we want to find the net area from 3 to 4. Well, we could use geometry here. What's the area of a circle of radius 1? It's pi r squared, pi times 1 squared. But we're only considering 1/4 of that circle. So we take the area of a circle of radius 1 and divide it by 4, and we get that the answer is pi over 4. And since all of this curve is above the x-axis, we don't have to worry about negative areas there.